네, 질문하시면 돼요.
그 위에 그냥 그림이 그 페르미온 제일 오른쪽에 있는 그림이랑 싱글렛 스테이트 그림이랑
네, 요거
그 화살표 방향이 그
방향은 상관없어요.
상관없죠.
예. 얘가 이제 업다운이든지 다운이든 업이든지 상관없고,
다리로 하면 된다.
예, 대신에 이제 그게 이제 이게 양자역학에서의 그 핵심이죠. 왜냐면 슈퍼포지션이, 예, 우리는 이제 그 고전적으로 생각을 하면은 그냥 업다운이냐 다운업이냐 뭐 그 정도의 우리가 머릿속으로 이해를 하는데, 수학적으로는 얘가 이제 플러스로 연결되느냐 마이너스로 연결되느냐, 얘가 그게 이제 슈퍼포지션의 모양이 어떻게 달라지느냐죠. 근데 그거는 이제 조금 그 양자역학의 핵심이 이제 슈퍼포지션이기 때문에. 예, 예, 좋은 질문이에요. 예. Here I will going on the interaction because and basically and the symmetric wave function or the spin symmetric or antisymmetric property is coming from the exchange of two particles. So and therefore we should think about the probability of the two particle exchange. So let's think about the exchange of two particles. And to calculate the exchange probability, and we should think that expectation value of the dispersion of particles. So dispersion of two particles is that x1 minus x2 square expectation is that it is separation of the two particles. X1 minus x2 is a separation of two particles, and the square and the expectation is a dispersion of the two particles. So here it is x1 square minus 2x1 x2 and plus x2 square. Then it is x1 square plus x2 square minus 2x1 x2. So and the expectation value of this x square or the x1 and x2 can be differentiated with the fermion or the bosonic case. Let's think about that the fermion state. In the bosonic case, it is trivial. In the bosonic case, it is symmetric between two identical exchange. And anyway, then in the fermion case, in the total wave function, it is symmetric and antisymmetric case, triplet case. Psi special part should be antisymmetric. In triplet state, it is a triplet state. So in the x1 square expectation should have the basis in the fermion case 1 to antisymmetric total wave function x1 square psi 1 to antisymmetric symmetric wave function. So it is psi 1 to special part antisymmetric and the spin part is triplet state. And the x1 square psi 1 to antisymmetric and the spin part is spin triplet. So here this we can write down psi 1 to antisymmetric and x1 square and psi 1 to antisymmetric in special part expectation. In the spin part it is normalized. Here let's denote that phi n at x1 is one particle at the quantum state n. For example, in the first particle, one particle at x1, it is quantum number 1. Denote that one x1 at x1 and the quantum number 1, whether at x2 and quantum number at x2 and quantum number 1, for example. So, and when you write down of the triplet state and psi 1 to antisymmetric wave function and x1 and x2, we already know that it is the 1 over square root 2 and phi 1 x1, phi 2 x2 and minus phi 1 x2 and phi 2 x1. So for simplicity, let's write down as 1 over square root 2. It is a quantum number 1 at at x1 and the quantum number 2 at x2 minus quantum number quantum number 2 at x1 and quantum number 1 at x2. So here from here, so it is 1 over square root 2, so it is 1 over 2, and it is 1 2 at 2 minus 1 2 2 1. It is x1, it is this one is that here, and x1 square and 1 1 2 2 minus 2 1 1 2. It is a psi 1 2 antisymmetric. So it is 1 over square root. When you apply this one to this one and this one, then 1 1 x1 square at one state, because x1 it is x1 applied to the at x1 and the 1 and 1, and the other one is that the 2 2 2 2 2. So it is applied here, applying this and 1 1 2 2, and x1 square is applied in the one state. So the other one is that apply here to here, then minus 1 1 x1 square and 2 1 apply here, and also 2 2 and 1 2. And the third one is that applying this one, then minus 2 1 2 2 and 1 2 x1 square 1 1, because x1 is that at one state at x1. And the final one is that applying this and this and this, then plus 2 1 1 2 2 1 2 x1 square 2 1. Here we should note that x1 is here 1 1, x1 is 1 1, x1 is 1 1 basis at 1 1. Then it is normalized, it is 1. Then it is from the orthogonality, and it is 0. And also it is also 0. It is 1. So it is 1 over here 1 x1 square and 1 1 plus, and 1 2 x1 square and 2 1 here. It is x1 square expectation. And let's think that here example we assume that it is infinite scale well. Infinite scale well of two particles, and the potential, it is the 0 and infinity at the x equal to 0 to L and otherwise. And from the single particle infinite scale well, the quantum state form is that 2 over L sine n pi x over L. So in the case for x expectation in the basis of nk is that n x and k, then it is integration from 0 to L phi n x x phi k x dx. And also x square n means that 0 to L phi n x x square phi n x dx. Then it is 0 to L x square phi n x square dx. Then from here phi x is sine function, so it is square means that 2 over L 0 to L x square sine square n pi x over L dx. So here let's denote it as a star. Then to calculate this, and let n pi x over L is y. I'm sorry. In this case, and the equation star, integration star is that x equal to L over n pi. So L over n pi x square and dx, so it is a cube. Integral 0. If x equal to L, then it is n pi. Is n pi and y square sine square y dy. Then it is L over n pi cube. Integration 0 to n pi y square. Sine square y is that 1 minus cosine 2y over 2 dy. So it is 1/2 L over n pi to the cube. Then y square, integration of the y 1/2 coming from outside, and y square is that y cube over third 0 to n pi minus here y square cosine 2y can be calculated like by the integration by parts. Integrate of the cosine and y square should be differentiated at first, and should be integrate cosine. So it is minus 1/2 y square sine 2i from 0 to n pi and plus, then differentiate with y square, so 2i, 2 cancel with each other, so 0 to n pi y sine 2i dy. Then because here n pi sine 2 n pi equal to 0 and sine 0 also 0, so it is a 0. Then it is 1/2 L over n pi to the cube, then n pi cube over 3, and also secondly, and this also should be calculated by integration by parts, integrate sine and differentiate y. At first integration sine to y and the minus minus 1/2 y cosine 2i from 0 to n pi plus plus 0 to n pi cosine 2i dy. Then if we integrate cosine 2i, then it is sine 2n pi and sine 0 also 0, so it is a 0. And also cosine 2n pi equal to 1. Cosine 2n pi equal to 1. And cosine 0 equal to 1. So 2n pi. Okay, then here n pi apply here. N pi, it is cosine n pi 2n pi equal to 1. But here 0 case and y equal to 0, so it is a 0. So it is in the first term 6 n pi cube cancel each other, L cube minus L over n pi cube and n pi okay. So then here therefore x square n equal to here and multiply 2 over L, so it is 1 over 3rd L square minus 2n square pi square L square. 맞네. Okay. And also, and x and n is that integration from 0 to L phi n star x and x phi n x dx, and it is 0 to L x phi n x square dx. Then from the phi function in the quantum infinite scale, well, it is 2 over L integration 0 to L x sine square n pi x over L dx. So let's denote as a 2 star. And then same, it is y, then 2 star becomes L over n pi x and dx square 0 to n pi y sine square y dy. Likewise, it is L over n pi square 0 to n pi y 1 minus cosine 2y dy. Then 1/2 L over n pi square y integration is that the y square over 2 0 to n pi minus here y cosine 2y also should be integration by parts, and also 1/2 y sine 2y sine 2i from 0 to n pi plus 1/2 0 to n pi, differentiate y, so sine 2i dy. Also this term is 0. Then the first term 1/4 n pi square cancel with each other, so L square minus 1/4 cosine 2i 0 to n phi, then it is 0 because 0 minus 0, so it is L square quarter. So x n is that L of 2. So we now calculated x square n. So let's think that at first distinguishable particles. Then distinguishable particles dispersion x1 minus x2 square, and distinguishable is that x square n plus x square k minus 2 xn xk. Then we already know that x square from here it is x square plus same but not n but k to k square, and minus xn x is the 2 L over 2 square. So it is L square, then 2/3 minus 1/2 minus 1 over 2 pi square, then 1 over n square plus 1 over k square, then it is L square 1 over 6 minus 1 over 2 pi square 1 over n square plus 1 over k square. Yeah. So it is a distinguishable particle dispersion. Then how about the fermion or boson case? Fermion F and boson B. Then x1 minus x2 square and boson or fermion. Then the dispersion is that x square n minus x square k minus 2 x n x k. Here fermion and boson case and should have the additional term. It is minus plus 2x and k and square. It is should have the external term. Then it should calculate, and this calculation is that x and k is that nx k state integration 0 to L x by kx dx. Then we can calculate from the square wave function. Then anyway, and by inserting I will skip the detailed calculation, and the detailed calculation very tedious, so I will write down the result. The result is that L over pi square 4nk over n square minus k square to the square and minus 1 to the n minus k minus 1. So, in the fermion and boson case, the dispersion x1 minus x2 square and boson and fermion, the result is that L square 1 over 6 minus 1 over 2 pi cube 2 pi square 1 over n square plus 1 over k square minus plus and 64 L square n square k square over pi to the 4 n square minus k square to the 4 and 1 minus 1 to the n minus k case. Here we consider for the n equal to 1 and k equal to 2. It is the first n equal to 1 is that the ground state, k equal to 2 is that the first excited state. So when we write down here for dispersion and the standard deviation of the x1 minus x2 square and the distinguishable particles is that by the calculation of the n equal to 1 and the k equal to 2 and the distinguishable particles is that the 0.32 L, and also same case and the x1 minus x2 square, and for bosonic particles is minus sign, then it is 0.20 L, In the fermion case, x1 minus x2 and the square for the fermion is that 0.41 L. Then it means that distinguishable particles, the probability is proportional to the probability, and proportional to the probability, and also here the fermion case. Dispersion, it is not probability but the dispersion, interparticle spacing, it is expected interparticle spacing. Interparticle spacing is very different in fermion's case, large compared to the boson or the distinguishable particles. In the bosonic case, in the bosonic particles has lowest possibility, lowest interparticle spacing. In the fermion case, in large, and they repel with each other. It means that with each other in fermion. So by calculating the probability density, and the probability density is that probability density is that for distinguishable probability x1 and x2 is that phi 1x and phi 2x and square, it is that 4 to the L square sine square pi x1 over L sine square 2 pi x2 over L, because n equal to 1 and k equal to 2. It is a distinguishable particles. And here symmetric particle, symmetric bosonic particle x1 and x2 is that square root 1 over square root 2, and the phi 1x x1 and the phi 2 x2 and plus phi 1 x2 and the phi 2 x1 square. You can insert here, and the phi 1 is that sine square, and it also sine square, it is also sine, sine and sine, sine, but it is x1, x2, x2, x1, and but we can write down in more detail later. And antisymmetric probability x1 and x2 is that same but minus sign. It is the same but it is minus sign. Then so by calculating this probability density, in the textbook there is a write down. It is the x1 and x1 minus x2. It is a probability of the x1 minus x2 case. And the distinguishable particles probability is like this. It is distinguishable. And symmetric particles probability is like this. And antisymmetric particle, the solution like this, antisymmetric. This antisymmetric means fermion. And there is no possibilities, zero possibilities. At the same position. So, and here is the result. The result probability considering between the relative coordinate is that the bosonic particle can be the probability is the most probable at the origin. It means that the bosonic particles can condense with each other. But in the antisymmetric fermion particles, and the zero possibilities at the origin, at the same position, because it is x1 minus x2. So, and there is no possibilities found at the same position, and they repel with each other. So this relative dispersion also fermion and repel with each other and far from with each other. But dispersion probability is the most probable, but the dispersion, it is a dispersion. Dispersion is small. In the also distinguishable, it is a dispersion is like this, and bosonic particle dispersion here, and the fermion case and dispersion is so large.